Hello and welcome to the Digital Creativity Lab here at Nokia in Munich. My name is Austin Please. I'm a research project manager at Nokia Standards. I will present you a demonstration on how to use vision-based positioning for creating digital twins, and the work has been done together with the Technical University of Munich. These days we hear a lot about digital twins for network planning and optimization, as well as for maintaining machines inside production environments, and also to enable extended reality services. But what do these digital twins consist of? And first of all, how are they created? A digital twin consists of very precise maps of the environment. But how can we create these kinds of detailed maps? Therefore, we need a very precise positioning system. In our case, what we are using a vision-based positioning system. This means that we use cameras for recording the environment. And you can see such a recording device over here. This is a rover which is equipped with a stereo camera, so a camera with two lenses, a small compute unit in the back, as well as a 5G connection to a nearby edge cloud. Why do we need a 5G connection? A 5G connection is needed because the vision-based positioning mechanism is quite demanding in terms of compute resources, and what we try to achieve is we try to distribute this load between the device and a nearby edge cloud. In our case, we placed the edge cloud behind our 5G standalone network, which is set up here locally. So this is a private network which we set up locally here within the DCL in Munich.
To create a detailed map of the environment, we first have to get the position of the recording device. Therefore, we are using the camera freed from the stereo camera, and in the first step do an image rectification to get rid of distortions. Next, we convert these two images from the left and the right lens into grayscale to be able to detect edges, so-called features. This is the next step, and there we take a single pixel and look at the surrounding pixels, and if the surrounding pixels differ significantly in terms of brightness, we identify a feature. Usually we find around 1000 features in each image, and with storing these features we already created a so-called feature map, and we can use this feature map to detect the position of any device by just comparing the seen features with the stored feature map. But as we are using stereo camera, we can also go to the next step. This is so-called feature matching. Here we take the left and the right camera image and merge these images together and compare the position of the feature on the left image with the feature on the right image. And by looking at the distance of the feature, we can detect whether this feature is close by the camera or whether it's far away. As the feature detection, the stereo matching, and the final creation of the feature map is quite resource demanding, we came up with the idea of distributing this processing pipeline between the rover and an edge cloud. This is what you can see here on this slide. So we have different options on how to distribute the processes. So we can either take just the camera images we see from the stereo camera and send them to the edge cloud and let the edge cloud do the rest, or we can do most of the processing also on the device and then only use the edge cloud for creating and storing the final feature maps. We now want to take a look how this split processing works in practice. Therefore, we set up an edge cloud and two devices called Eckehard and Marco. And you can see here that we also plot some statistics. In this case, it's the CPU load of all three devices. And for the rovers, we also plotted in addition the required bandwidth on the air interface as well as the latency. Below these statistics, you can see what is currently received at the edge cloud. So how do we already do this split processing? And you can see that it's set to matches raw. This means that I do everything until the final mapping and tracking on the devices and just send the matches in raw format to the edge cloud. On the right hand side, what you can see is the already created map for the two devices. and you can identify there certain number of features. Let us now change the mode from matches raw to video and take a look at the impact on the latency as well as the bandwidth and CPU load. Video mode means that I'm now just taking the images from the recording device and send these images to the edge cloud and let the edge cloud do the rest. What you can immediately see is the impact, and here the latency decreases as well as also the bandwidth requirement decreases. The reason for the bandwidth requirement decrease is that the video compression mechanisms are very, very effective, and so we do not need that much bandwidth on the air interface. But you can also see the impact on the CPU load, so that the CPU load on the devices decrease. Now in the next step, we want to set it to features, meaning that I also detect the features on the device and let the edge cloud do the rest. And you can also see immediately the latency, bandwidth, and CPU load increases. The reason for this is obvious, that I now have to detect the features, so that's why the CPU load increases and also the bandwidth requirements and latency increases, because the features also have to be compressed and the compression mechanism is not as good as a video compression mechanism. Now let's do a similar thing for Marco. We have until now sent the matches in a raw format, so I did not compress any of these matched features. And I switch it now to matches with compression, and you can see that the bandwidth requirements on the interface decrease because the features are compressed. But of course, the latency increases a bit because I still have to run the compression algorithm on the devices. With this demonstration, we've seen on how to split the processing between a device and a nearby edge cloud to create these feature maps, which you can see here on the slide. So we created a feature map of the Digital Creativity Lab and also marked there with the blue-green path. This is the path with the rover which we've taken. With this map, you cannot identify, that this is really the Digital Creativity Lab, but this can already be used by the rovers to autonomously navigate within this Digital Creativity Lab. To be able to also identify what are the different objects, we then use this sparse point cloud to create a dense point cloud, which you can see here on the slide. And on this slide, you can already identify the different components which are placed inside the Digital Creativity Lab. In addition, what you can also do is you can combine these different maps, so the sparse feature map, the dense point cloud, with also a building information model or CAD model, which you can see here. And all these different map layers form together a digital twin. So digital twin consists of several different layers, which you can see here on this slide. So we have various layers. In this case, these are 6 layers. So you can also include some semantic layers with all the marked objects. And you can, of course, also include there a network topology map. So we've seen on how to create these digital twins, and we've already mentioned that you can use these digital twins for various application scenarios. But what has to be mentioned is that you also need a very intelligent map management system, so that you have to update the maps in more or less real time, that you also have to take care of the size of the map and also of privacy aspects.
So within this demonstration, we've seen on how to create digital twins making use of cameras. In our case, these cameras were mounted on such kind of rovers. But what we've also seen is that the creation and maintenance of digital twins require some computational resources. So in our case, what we did is we distributed the load for processing the camera images and creation of digital twins between these rovers and the nearby edge cloud, making use of a powerful 5G standalone network, which we set up here locally within the Digital Creativity Lab. With this said, I'd like to thank you for your attention and hope to see you soon.